And hello everyone on YouTube. Welcome back to this video of convection boundary layers. So the last video we actually derived our form of the convection boundary layer equation using our integral boundary layer expression. Now the question is, how then do you want to solve this? Okay, how do you then solve this? So okay, the way we did it, or the way that Paulhausen did it, was to assume a power series expansion, a cubic expansion for velocity. Okay, so this was our velocity profile based on the boundary conditions we had before, and so we found a velocity profile previously. I think yeah, based on this was in past videos. I can't remember where I put it at the moment. Okay, it's not here. Must be in my fluid mechanics videos. Okay, but more or less, based on the boundary conditions, you will get this form of equation here. Okay, so a velocity profile would be something of this form over here. U over u infinity equals to 3 over 2y over delta p minus half y over delta p cubed. Alright, so what do we have here? Yeah, what do we have here? Okay, so we have this boundary, we have these equations, and they are actually derived with the boundary conditions. Okay, u equals to 0 at y equals to 0. That's one. Okay, next it's u equals to, okay, let me put some equations down on that. Okay, u infinity. Okay, and I'll have to put proper spacing here. Okay, u equals u infinity at y equals to delta t, or well, y equals to delta p. So these are momentum boundary layer. Next, it will be that next thing is that near the boundary layer, okay, near the boundary layer, partial u partial y equals to 0. There's no shear stress at the boundary layer. Okay, no shear, no y shear stress, or no x shear stress near the boundary layer. So let's compile this. There's one more, and also the shear stress profile. Okay, the shear stress profile near the boundary layer is linear. At y equals 0. Okay. So the shear stress profile near the boundary layer, the shear stress at the boundary layer is pretty much 0. Shear stress profile near your surface is linear. Okay, your shear stress profile near the surface is linear. That's why you have this del 2u del y squared equals to 0. Okay, so now we apply the same thing. Okay, we apply the same thing for temperature. Okay, so the key difference here is that we have T minus Ts instead of just T itself. Okay, because the velocity of the surface is 0, so u minus us will still be like u. Okay, so this is what we need to take note: the temperature difference between the fluid and the surface temperature. Okay, and let's write this down. This a plus by plus cy squared plus dy cubed. All right. Okay, so we assume this kind of velocity profile for u, and then with these boundary conditions we get this expression. Now that was done with the hydrodynamic boundary layers. Okay, so we're going to apply similar BCs, and let's take a look. If we replace U by T minus Ts and dP by the dt, delta T, which is the thermal boundary layer, will all these still hold? I mean, if it holds, it'll be very convenient for us. So let's see. T minus Ts equals 0 at y equals 0. Let's try that. T minus Ts equals to 0 at y equals to 0. Yeah, T minus Ts equals 0 at y equals 0. Does it make sense? Absolutely, because T equals to Ts at the surface. So that checks out. Let's try the next one. T minus Ts equals to T infinity minus Ts at y equals to delta T. So now let's see whether this works. So T equals to T infinity at the boundary layer. That also checks out. Okay, next thing, partial T minus Ts, partial y equals to 0 at y equals to delta T. And what is this saying? This is saying that the heat conduction, okay, the heat conduction near the boundary layer. So I'm gonna. Oh, I don't have a diagram now. Great. Okay. What is this saying? This is saying that the heat conduction. Let's see. GIMP. Put some of my marks aside. Okay. So again, we have our thermal boundary layer. Okay, so this is partial T, partial Y, right? Which is going to represent the heat flux here. So we're gonna the conduction heat flux. So it's conduction heat flux, just to be very clear. So the conduction heat flux at this boundary layer over here is very much 0. Okay, we neglected conduction for all surfaces except the fluids which is in direct contact with the surface over here. Right, this is a surface. Oopsie, we need to switch back to turquoise or cyan. Oopsie, this is the surface. Okay, so heat flux at conduction heat flux at all these other points is pretty much 0 except the heat conduction at the surface. So that's fine. Okay, this still checks out. Next thing, it's a bigger assumption, I would say. Okay, del 2T minus Ts del y squared equals to 0 at y equals to 0. This is a slightly bigger assumption, but it's not too hard to see, not too difficult to see that well, you will have some sort of an oh, did I just put del square y? Oops. Yeah, it's not too hard to see that maybe very near the surface, the boundary, very near the surface. I mean, the heat flux can be constant. Okay, heat flux is constant. What last one is saying? Last BC is saying near the wall, heat flux is constant. Okay, so that's the equivalent. And of course, this boundary condition here is saying near the wall, the shear stress near the wall shear stress is constant. Alright, so that's that. Okay, so let's continue there. So these are not really really outlandish what do you call that? These are not outlandish assumptions to make. Okay, so if you notice, if we replace u by t minus ts here, and of course u infinity by t infinity minus ts, and delta p by this delta t thermal boundary layer, we find that these boundary conditions actually apply to this cubic form of equation in the same way that if we were to assume u equals to a plus by plus cy squared plus dy cubed. Now, if we assume that, we will get this velocity profile. So we kind of think that these profiles are analogous. Okay, let me do it again just for clarity. So okay, we got this expression over here for the velocity. All right, we got this expression here for the velocity using these boundary conditions, and assuming, okay, u equals to a plus by plus cy squared plus dy cubed. Okay, so we assume these two. Okay, so we assume these boundary conditions and this velocity profile. We put both of them together. I mean, if you watch the fluid mechanics video I posted up, you put both of them together, you will get this velocity profile. Now if we do the same thing, okay, if we replace u here by t minus ts, u infinity by t infinity minus ts, and all the y, wherever you see delta p, you just replace it with delta t, you'll get exactly the same expression. Okay, so if you do the same thing for temperature profile, you will get the following expression: t minus ts, okay, over t infinity minus ts. Okay, it's equal to, okay, I'll just copy and paste all of this here. Put it here. Let's put delta t. Okay. So you will get this velocity temperature profile. Okay, not too bad now, not too bad. You have something in terms of y, and now you can actually plug that back in here. So let's try substituting these back into our integral boundary layer equation. Of course, if need be, we know our delta p, which is the momentum boundary layer over x, equals to this following expression based on our what do you call that? Based on our hydrodynamic boundary layer. So in case we already know for how this boundary layer thickness actually changes with x. Okay, no problem. So let's substitute back. Okay, I'm going to paste it twice as usual so that we know where we are starting from, and then we can start to change from there. So okay, I paste it twice. So first thing we want to do is assume, okay, t infinity is constant. with respect to x. Now this is not always true, but in the most simple flat plate case with constant temperature surface and constant temperature free stream, this will be the case. This is the most simple case of this convection boundary layer. Okay. Now I think the equations are rather easy, relatively speaking. So what do we do here? We'll need to substitute the expressions for u and t minus t infinity in. So what do? We have to substitute the profiles in. Okay, I have to substitute the profiles in. So let's first substitute the velocity. Okay, so what's the velocity profile? Velocity profile is on top here. So this is the velocity profile. Of course, we'll need to multiply it by u infinity, which we can just leave it outside. Now we'll need to do the same for the temperature profile. Okay, we'll need to do the same for the temperature profile. And now notice that there will be two boundary layers here. Okay, there will be two boundary layers here. One is unfortunately you have two boundary layers here. One is the thermal boundary layer, and the other is the what do you call that? The momentum boundary layer. So we'll need to put that in. So okay, so this is t minus t infinity. So we'll kind of need to swap it around, so to speak. Okay, let's see. Okay, so this is not in the format of t minus ts. It's rather t minus t infinity. So doesn't look too nice to substitute in here just yet. But well, I guess you can just substitute in lock, stock, barrel, meaning to say I make t the subject of this equation. Okay, I make t the subject of this equation, and I just substitute everything in lock, stock, and barrel. Okay, so it may or may not work. It may get very messy, but let's try anyway. T equals to ts plus, okay, this whole thing here. This whole thing here, and then you get t infinity minus ts. Okay, so I'm going to shift t infinity minus ts to the right hand side, and then you add ts to both sides. So that's your temperature profile. Okay, so we can put that in. So we substitute in this. Let's check the time. Okay, I'll do a few more substitutions and that's it. Okay, so we can actually substitute this into both sides, both the left and the right. Okay, so wow, it's a little bit daunting to me looking at this. Oh, but good thing we can actually factorize some things out later. Okay, some things we can actually factorize out later. Okay, so let's substitute both of these to the left and the right hand side. Okay, so the left hand side, and let's do the right hand side as well, which will obviously spill off the page. Maybe I'll just do the left hand side first. I'll just do the left hand side because yeah, it's gonna get very messy very quickly. Okay, so you see how messy it gets, but one thing to note, you can bring the t infinity forward. Okay, bring the t infinity forward. So t infinity is on the right hand side here. You bring that forward. So okay, You bring this forward, and then you can factorize out the Ts minus T infinity. Okay, you can factorize out Ts minus T infinity. So I'm going to multiply a minus 1 in there to try and change the signs. Let's see. I'm going to multiply this in here. I'm going to change these signs. So Ts gone. I'm losing count of the brackets. There's too many there are too many brackets there. So one parentheses, two parentheses, two parentheses. Okay, so I think they're double brackets which are like redundant. Let me get rid of the double brackets. Okay. Now we are good to go. You can see that we can factorize out this Ts minus T infinity outside. Okay, so we factorize that out, Ts minus T infinity. And let's bring this to the front. Okay. And yeah. Okay, not too bad. So we can actually make the assertion. We can assert that these two are independent of both y and x, because these are just constants. So we'll just bring them out to the outside. You just bring them all the way out to the outside. Yeah. So that we don't have to worry about them at all. In fact, we can divide both sides by Ts minus T infinity. We can divide both sides by Ts minus T infinity, so that the right hand side you can just have this. Okay. Okay. So divide both sides by Ts minus T infinity, and then you can substitute the right hand side with theta, where theta equals to T minus Ts, T infinity minus Ts. So it's a very quick way to get rid of this Ts minus T infinity, and you get theta on the right hand side. You shorten everything for sure. Of course, when I divide throughout, you notice that Ts is negative at the bottom. So I took out the minus signs. Okay, I took out the minus signs. Maybe I'll do it this way. Yeah. Minus Ts minus infinity, so that it's clearer for you. So I divide both sides by minus. Actually, no. That's bad. Just Ts minus T infinity. Okay, so this minus sign actually gets absorbed into the theta. Okay, let me put the intermediate steps and I'll call it a day. Yeah. So I have a minus alpha here. And this is T, of course, which I can put T minus Ts, which is the same thing. Okay. 1 over Ts minus T infinity. Okay, so I'll do that, and I'll just swap the signs around. Swapping the signs around. T infinity minus Ts. And then I can just multiply this in to get theta, which is the dimensionless temperature, which we were talking about earlier. This kind of dimensionless temperature profile. This is theta, yeah? This is theta. Okay, not too bad. At least this is tidied up, and I have to remove the Ts minus T infinity all the way at the bottom. Okay, now we are good. We are good. Okay, now the thing is, of course, we need to deal with this one term at a time. Unfortunately, but that's life. We got to deal with that. Okay, so I'll see you guys next time. Thanks for watching. We'll continue discussion after. Thanks.